This is a demonstration of a new product for visualization of gross pathology such as epilepsy or strokes, tumors, and other disorders that can be seen in the human EEG. On the left is a real-time streaming of EEG from an epileptic patient, a 13-year-old female. And one can change the time scale if one wishes. On the right is a visualization tool called the NeuroNavigator. This particular tool has a lot of flexibility, and I'll be going through it, and can be used as a standalone, in that you can record EEG and then import it into NeuroGuide and evaluate the patient's EEG in detail, and determine information about the sources of an epileptic focus or a gross pathology. One can also do the real-time evaluation like I'm doing here, or a time domain capture where you can look at time point by time point, digital time point of the sources and the effects of a pathology on different networks of the brain. We'll also have this available as a dynamic link library, a DLL, that can be used or incorporated, integrated within a given EEG manufacturer's software itself, similar to what Persist does. So it's an analytical tool. Once an epileptic or a focus is determined or a gross pathology is identified, then one can drill down with this type of Hubble telescope in a way and see much more detail about the nature of the pathology itself. There's coronal, sagittal, and axial slices as I rotate the brain here. Now, I can change a lot of different things, and I'm going to go through some of them right now. For example, we can just look at the axial view, just the coronal view, sagittal, the volume view, change the size of the volume view, the 3 view up here, 4 view, and then the view I was just showing. One can add different slices and navigate through the brain if one wishes. And with the Brodmann areas and Telerik Atlas coordinates that are standardized through the National Institutes of Health and the International Consortium for Brain Mapping. I'm going to remove some of these slices for now and just keep the axial slice. And we're going to look at the connectivity, and we can also change the transparency of the head model, and for example, or remove it completely. And we can also eliminate the cortex or make it more or less transparent. I've selected the language network. I'm going to add the head model back so there's some, it helps to have a reference. And we can also look at the scalp if we wish to look at the electrical potentials at the scalp in real time or offline. This is the language network in the left hemisphere of this individual, in which the hubs are Brodmann areas, and the language network is determined by PET scans, functional MRI, and published in numerous papers and by numerous people, and established primarily funded by the National Institutes of Health through the Human Brain Mapping Program. We can also evaluate different networks. We can look at the dorsal attention network, for example. And what we're looking at here is coherence between the hubs of the dorsal attention network. We can look at other networks, of course, but we can also look at lag coherence, which is a measure of coherence that's independent of the volume conduction. And we can look at phase delays, as well as phase slope index, which is information flow. These are phase delays. You can see the value of the phase differences in degrees in the lower left here. That's the scale that shows what we're interested in terms of absolute values. There is the ability to evaluate this in with respect to an age-matched normative database. I'm now going to turn on the diffusion tensor imaging. This is the Collins 27 brain from the Montreal Neurological Institute that can be downloaded from the internet. It has 1 millimeter resolution in the MRI, and the diffusion tensor imaging is the ICBM 52, again, the Collins brain. It's the International Consortium for Brain Mapping, which was downloaded from the Loney Institute at UCLA, and it's a standardized diffusion tensor imaging. But the colors of the diffusion tensor imaging change according to the value of the coherence or the connectivity that we're looking at. Let's go back to the language network, because this individual's symptoms and consequences of the focal left temporal lobe epileptic discharge was largely on language, as well as executive function and some frontal lobe disorders. Right hemisphere was quite normal in this individual. This was used, this EEG, for surgical planning by evaluating the right hemisphere, and because the child was 13 years of age, eventually the decision was made not to remove the focus and instead to treat the patient in other ways. The value of this particular visualization tool is multiple. It can be used for neurosurgical planning. It can be used for pre and post treatment evaluation. It can be used for planning for RTMS, as well as pre and post RTMS treatment. It has great flexibility. One can evaluate different frequency bands wherever one wants. One can evaluate Z-scores, or just in this case, it's just the Z-scores, and one can just look at different fiber bundles. I'm again going to look at the raw scores of the diffusion tensor imaging. And also, as I remove the head model, we have the ability to look at connectivity, functional and effective connectivity involving the cerebellum, the thalamus, the benula, the subthalamus, and other parts of the brain, partly because we have very high resolution here. This is SW Loretta. It's using 12,270 voxels for the cortex. With the cerebellum, there's more voxels. And it uses boundary element method to localize sources and does not use a spherical head model, so it has high accuracy and can be saved as an image file, or it can be saved as a digital file for statistical analyses if one wants. So this will be available to view at our booth 101 at the American Academy of Neurology. We welcome you to visit. We look forward to demonstrating this new visualization tool and finding ways to integrate with existing EEG software companies, and including with DLL, so it's integrated and can complement the existing tools that neurologists have to better evaluate their patients and to find better treatments. So thank you for watching.